So good morning everyone. Welcome to Kaexchem, and in this lecture we will be covering general organic chemistry, but only the first part of it, like the electron displacement effects and stuff, because well, this is a huge chapter, so it will take me some time. So don't mind if this chapter is cut into 2 or more parts. It will all be worth it. So let's begin. Just know that this is not for first timers, but if you are a first timer, well, you can proceed if you have read this chapter at least once before, or let me just say you need to know what electrophilic aromatic substitution is. The rest I will tell you. So let's begin without wastage of time. So these are the basics. You must know about bond fission. All organic reactions involve bond fission. How will reaction happen without the breaking of bonds? And this is homolytic fission, in which we use half arrows, also known as fishhook arrows, to convey that a homolytic fission has taken place. And there are 2 electrons in this bond, and they equally distribute between the 2 atoms. And in homolytic fission, there is no condition of electronegativity between the 2 atoms, but it is preferred if they both have similar electronegativities, although it doesn't matter much. Any bond breaking is an endothermic process, and this homolytic bond fission, it forms a radical. This is known as a radical, in which there isn't a plus or minus charge, but instead there is a free electron in the atom's valence shell. And homolytic fission is preferred in gas phase or non-polar solvent, because in polar solvent it will tend to separate them as ions instead of radicals, and usually heat, electricity, or light is used as an energy source in homolytic fissions. And peroxides are usually present because this OO bond is very weak and it can break into 2 radicals. Now, heat-lytic fission, easy to understand. One atom takes both of these electrons and gains a negative charge. Here, A is more electronegative because it took both the electrons. And this again is an endothermic process, but it forms ions. And for this, a polar protic solvent is preferred, just as I told you. A polar protic solvent helps in stabilizing these ions by adding negative charge here and positive charge here, like the solvent will surround the negative charge with the positively charged part of the solvent, and this is known as solvation. And this bond breaking requires more energy than homolytic fission, and this is usually happening at low temperatures in solution. Okay. Now let's learn about reaction intermediates. These are the species which may show up in between of the actions. Like these can never be the final or initial reactant, nor they can be the final product. But these may show up in between of the reaction, and learning about these helps us understand how the reaction has taken place and, to an extent, predict the products of the reaction. Now, a carbocation, all of you know, the central atom carbon is sp2 hybridized, trivalent. It has incomplete octet, 6 electrons instead of 8. It is unstable and reactive. All intermediates are unstable and reactive. It has a vacant p orbital because this was sp2, and any atom has 3 p subshells. So one p is vacant here, like this. So this is the vacant p orbital. This acts like a Lewis acid. It can take in electrons, and since it wants electrons, we can consider it electrophilic. And this is diamagnetic, as all these electrons are paired. Okay. Now, and also this is known as carbenium ion. It's trigonal planar, and the bond angle between 2 hydrogen atoms is 120 degrees as expected. Now, if we learn about carbon ion has hybridization sp3. All its bond angles between the hydrogens is less than 107 degrees, and its shape is trigonal pyramidal because this lone pair has greater repulsion than the bond pair, and it pushes them down here. So it is trivalent, but this time it has a complete octet because it has 2, 2, 2, and 2 more, so complete 8 electrons in its octet. Again, unstable and reactive. It has no vacant p orbitals. It acts as a Lewis base and a nucleophile because now it wants to donate electrons. And again, this is diamagnetic because all its electrons are paired. Now, if we learn about free radicals, they are very similar to carbocations. Their bond angle is 120 degrees. And instead of a lone pair, they just have a lone. They just have a single electron chilling in an orbital. And trigonal planar shape, of course. Again, sp2, just like carbocation, the electrophiles. This is trivalent, incomplete, unstable, reactive. We know that. No vacant p orbital is something you need to pay attention to because the p orbital has been taken by the single extra electron. And since this electron is not paired, it is neither a Lewis acid nor a Lewis base, and also it is paramagnetic. And its magnetic moment is √3 Bohr magnetons. Okay. Now these are some extra intermediates. Just go through them if you want to. Knowing about these is not important. I just added them to fill the space. Just go through them from the notes. They are not important at all. But now let's start learning about electron displacement effects. And most of you already know about this, but let's do a quick rundown. What is inductive effect? It is permanent pull or push of sigma electron density, sigma, not pi. It does not affect pi electrons that much. And electron density, it always happens in a covalent bond. And since it's an effect, it must always happen due to an atom or a group. Okay. And this is a permanent effect, as I mentioned in the first word of the line. And if the group pulls electrons, we call it minus I effect. And if it pushes electrons, we call them plus I effect. The inductive effect is the only permanent effect which is distance dependent, and it happens due to difference in electronegativity. For example, see, this is how it happens. If this is a highly electronegative atom, electronegative atoms have a tendency to pull electrons towards them, and hence the one which is directly attached to it, it pulls the electrons with a great force. The one which is later, like it comes later in the series, lesser force, then again the next one lesser force, and it is ignored after 4 carbon atoms. And the same thing can be said for the plus I effect. This is now a positive electropositive atom as compared to carbon. Okay. Now, when we compare two situations, I'll tell you what situations means. We have to check in order of distance, number, and power. How? What do you mean? Well, for example, if I tell you a question that I will show you two situations, and in each part of the what word have I written? Oh, in each part of the circle site, tell which case has more I effect. Only talking about the magnitude. Well, this is the circle site. Now we have to compare which part is giving more inductive effect. So first we see distance. Are both the groups equal distance? No, they are not. Since this is further away, this will always have greater inductive effect. Now here we see that both of them are at the same distance from the circle site. So now since distance is same in both cases, we will now look at number. We see fluorine and there are 2 iodine here, but only 1 fluorine. So since there's more iodine, this will have greater inductive effect. And look at this. They are at the same distance. They have the same number. Now what do? Now we will check the power series. You have to remember the power series of minus I and plus I effect separately. Sorry, there's nothing much you can do. But I have written the orders. Just read this every morning and you will be done with no time. Just have some tricks to learn it quickly. See, all the top ones are nitrogen. All the halogens are together. Just do it, okay? And here we see that tritium has more inductive effect than deuterium. So again, since distance and number is same, we now check the power series, okay? And remember this point, the plus I effect of silyl is greater than methyl because they have less electronegativity, silicon, okay? Now moving on, we will now see resonance or mesomerism. What is resonance? We saw inductive was of sigma electrons, but resonance is permanent delocalization of pi electrons in an electron cloud, which belongs to parallel p orbitals. How is that electron cloud formed? See, this is benzene. This is another conformation of benzene. No, sorry, another resonance structure of benzene. But these are only individual structures. They don't show the full picture. But if we combine these structures, we can form a hybrid. And this hybrid shows us what benzene really is. These are all, they are not single or double bonds. These are 1.5 bonds. Okay. And all the electrons are basically in this cloud here over the plane of carbon atoms. And this is what we call as mesomerism or resonance. Okay. And this causes more than one possible structure to exist for a compound, just as we saw. And both of these structures cannot explain all of its properties by itself. And their hybrid shows the full picture of the compound. Just keep this as a fact in mind that more stable resonating structure contributes more to hybrid. Yes, different resonating structures have different stabilities. And more stable the resonating structure is, more it will contribute to the hybrid. Okay. This is necessary condition for resonance. A neutral compound must have minimum 3 parallel p orbitals. These are parallel p orbitals. And ion must have minimum 2 parallel p orbitals. If an sp3 atom with a lone pair is next to a parallel p orbital, then the lone pair can delocalize. For example, we see that this is sp3, there's a lone pair, this lone pair cannot delocalize. Again, this is sp3. This lone pair cannot delocalize. But the moment we made this carbon, the one right next to the parallel p orbital, there's a lone pair. So now it can delocalize like this. Okay. And if an atom has multiple lone pairs, only one will delocalize. For example, let's say there was another lone pair here. This was some magic atom. On still, only one lone pair would delocalize in this case, and the other one would stay localized. Okay. And just learn how to draw molecular orbital diagrams. For example, I can show you any compound, and you must be able to draw the molecular diagram of the p orbitals. For example, just look at these. How you can see that in vinyl chloride. This is sp2, so of course it must have a vacant p orbital here. And chlorine must store one of its lone pairs in the p orbital, and all of this forms a conjugation with each other, and resonance takes place. Look at all of these examples once. Now we move on to resonance structure. I'm sure you must already know how to draw resonance structure, so I'll just give you some extra points. Always follow the octet rule. For example, look at this. This resonance structure is invalid as here nitrogen is forming 5 bonds. But here we see that there is no issue because it can form 4 bonds. Any second period can form up to 4 bonds. And here we see that it's forming 5 bonds. So this is invalid while these two are valid. Next, never and ever move an atom in resonance structures. Only electrons will move, only bonds will move. Same thing. But atom itself will never move. Because if an atom moves, that comes under tautomerism and not resonance. Okay. And each resonance structure must have the same unpaired electrons. For example, these two have the same number of unpaired electrons. This can't be a valid structure because here there are 2 more unpaired electrons than in the original structure, and hence this is invalid. Adjacent atoms cannot have opposite charges. Why so? Because this is chemically, so mathematically, physically. Oh, I can say chemically. What is chemically? Anyhow, this is equivalent to this. Okay. Like this thing just attacks here and it forms a bond. This can never exist. And it always exists as a bond. So adjacent atoms cannot have opposite charges. The best they can do is have small positive, small negative, but not like this. Okay. So stability. I told you that more stable resonating structure contributes more to the hybrid. So how do we know which resonance structure is more stable? So we need to know that. Sorry, my throat. Yeah, so as I said, but we need to know that the resonance structures can have different stabilities to each other, and how do we check that stability? First of all, we must know all the resonance structures of a compound, and once we have all of them in front of us like a list, the one which has, we will check in order. Like this rule, if this rule allows us to sort all of them, then we will not look at the other rules. But you understand my point, right? We will look at this first. If 2 or more have this same, then we look at the second. If this is same, then this, and then this. Okay. So first of all, we will say which resonating structure has more atoms with 8 electrons, like full octet. Okay. If we see that all of them have the same number of fully loaded atoms, then we look which of them has the most covalent bonds. And if you think about it, both of these rules are more or less equivalent, but still I've written them separate. Next, we will check the negative charge should be on or close to more electronegative atom. If this is also same in 2 or more compounds, in 2 or more structures, then we move on to unlike charges should be closer. Why? So that they can neutralize each other. Unlike charges should be far away so they can't repel each other. And if all of these factors are the same, we then check which compound has more benzenoid rings. What is benzenoid rings? This only applies to compounds like phenanthrene and anthracene. Basically, this is a benzenoid ring. And if it's, say it's joined to a cyclohexane ring like this, another cyclohexane ring. So this is not a benzenoid ring, this is not a benzenoid ring, but this is a benzenoid ring. Okay. I also have an illustration to show you. For example, if we know these are resonance structures that have been given and we have to rank them in stability. So see the workflow. I have not written the answer directly. I have written the workflow first. What do we see first? We see that one must definitely be the most stable resonance structure because we know it is the neutral one. And do I need to write that charges make anything unstable? But okay. First is the most stable resonating structure, and then we see compare the other three. Then we see that 2 is more stable than 3 and 4 because all of its atoms have 8 electrons while these do not because of this is 6, this is 6. And finally, we see that 4 is more stable than 3 because here the negative charge is closer to more electronegative atom, just like we saw. And this means 1, 2, 4, 3 is the correct answer. These are some extra points about resonance. Well, sorry, I had to pause because I went to drink tea. Let's continue now and let me change color. Yeah, so these are some extra points about resonance. In analogous compounds, for example, compounds that have the same number of parallel p orbitals and look similar to each other, cross resonance is less stable than extended resonance. What are these terms? I have never heard of them. Listen, cross resonance is one lone pair is busy with p orbitals on more than one side. For example, say this lone pair, it has two ways to conjugate, the left double bond or the right double bond. But the one on the right side has only one way and it can conjugate all the way to here. Okay. So this is extended resonance and this is cross resonance. Okay. So in analogous compounds, the cross resonance is less stable. I think that's easy to understand. And resonance structures are hypothetical. They are not real. And the compound stays in one form, which is a hybrid form only. I just told you this is a real picture, the full picture of the compound. And this is basically the mechanism of how electrophilic aromatic substitution works. It is important for understanding the next two topics. So just see. The electrophile here, it sees that it looks at benzene, looks at this electron cloud here, and it sees that, wow, there's electron density here. I want electrons. So it goes and attacks the benzene and it breaks one of the double bonds and gets joined in place of it. And then it kicks out the hydrogen, the proton here, and there's now no hydrogen here, and it has taken place of the hydrogen that was there. For example, this is C6H6, right? So now this is C6H5E. Okay. So just keep in mind, this is what electrophilic substitution is. Now we move. Now this was, I just told you about resonance. Resonance in itself is not an electron displacement effect. But when that resonance is caused by an atom or a group, which is added to a ring, then it is called the resonance effect. For example, all compounds with resonance need not have resonance effect. And plus or minus R effect or plus minus M effect is basically pushing plus or pulling minus electron density by an external atom or group in an already conjugated system. To understand this, we did an experiment. How? We looked at normal benzene, then we looked at two compounds, aniline and nitrobenzene. Okay, label them A and B. Now, if we let each carbon of benzene have an electron density is equal to X. For example, each carbon has an electron density equal to X. So when we added NH2 here, we saw that the electron density at the carbon, which is two carbons away from the point of addition of NH2, it had the same electron density, but and just this is called the ortho position, this is meta position, and this is para position. So only the carbon atoms at ortho and para position were affected by NH2 and their electron density increased from the baseline of X. But when we added NO2 here, their electron density decreased from the baseline of X while the one at meta position remained same. Why is this and what is happening? Well, some groups tend to increase or decrease electron density at the second or fourth position from the group's position, ortho and para respectively. And as I told you, the third position is ignored completely. Now, remember I told you about electrophilic substitution. So, in electrophilic substitution, the plus R effect causes the electrophile to prefer para position, then ortho position, then meta position. Actually, meta is negligible for substitution, and para is the major product in most cases, ortho is minor, and this we call the plus R effect. We call it ortho and para directing, and vice versa, the negative R effect causes electrophile to prefer the meta position. Why? Because it reduces electron density here. So if an electrophile comes here, so it wants to attack the one with the most electron density. Keep in mind, minus R does not increase electron density in the meta position. All it does is reduce the others. So to the electrophile, the meta position seems the most attractive. Okay. If there's a group which can show both plus and minus R effect, these are groups that can show both plus R and minus R, then plus R is preferred because plus R is a stabilizing and octet filling effect. And a group is said to have activating effect if it encourages electrophile to attack. Okay, I hope that's easy to understand. And deactivating if it discourages them. Basically, if it increases electron density, it is activating. If it decreases, it is deactivating. And activating effects are orthoparadirecting, deactivating effects are metadirecting. But there's an exception here, which are the halogens. Halogens are orthoparadirecting, but they're also deactivating at the same time. How did that happen? Basically, they give electrons by plus R. So when the electron has to attack, it sees the effect of the plus R and attacks at the ortho, para positions, but the net electron density from the ring has been withdrawn. Why? Because halogens are highly electronegative. They take back by minus I effect. So net electron density decreases. But still, if an electrophile does attack, it is directed to ortho and para position. Now, how do we know that which groups are activating, deactivating? How do we know? Basically, this is a screenshot from my notes, and light had gone, but I still wanted to write. So this is just paper here. The highly activating groups will be those ones which have unhindered lone pair. We will understand what unhindered means. Unhindered means is basically hindered lone pair means that, again, you see this is cross resonance, as I told you. It is busy in two sides. It is resonating among itself. And when you add it, it cannot give much attention to the benzene ring here. Okay. So it is mildly activating. And the groups in which the lone pair is not busy, we call them highly activating, like these groups. These are mildly activating. Some groups are lowly activating, that their activation is not significant, but they're still activating. And those are alkyl groups. And they activate by plus I or plus H, not plus R. Alkyl groups do not have lone pairs. So they do it by plus I or plus H. Okay. We'll understand what H is. And halogens have a mildly deactivating effect, just I told you here. And see, as I told you, the halogens are ortho and para-directing. So everything here, highly activating, mildly activating, low activating, and mild deactivating. All of them are ortho and para-directing. Now we look at medium deactivation. Again, it's the case of cross resonance here. You can see that it is also taking electrons from here and also from here. So it can't focus on our benzene ring. And the highly deactivating ones are the ones which are not engaged in cross resonance and can focus on the benzene ring, which are these groups. Okay. Now we learn about hyperconjugation. First is an experiment basically. We took 4 compounds. This is toluene, this is methyl toluene, dimethyl toluene, trimethyl toluene. Well, if we don't know hyperconjugation, then which of these compounds do you think will be most encouraging for the electrophile to attack? You would say, since this has the highest positive I effect, then electrophile must be tempted to act here. You are filling the trap. Since I effect is highest in D, it should be the best at allowing electrophile to attack, right? No, that's wrong. How? It turns out the actual best electrophile here is the first one. How? And the order is A, B, C, D, which means this is better than this is better than this. How does that happen? Basically, you know the ring has parallel p orbitals like this. These parallel p orbitals of the ring can sometimes conjugate with the XH bond if X is sp3. Well, consider this CH bond. This is a CH bond, C is sp3 here. So this CH bond here, basically this can sometimes conjugate with the parallel orbitals like this. Okay. And this causes a stabilizing effect. Here you can see that this has no hydrogens. So this does not do hyperconjugation, but this does. This does it less because it has lesser hydrogen. This does it even lesser because it has only one hydrogen, and this doesn't because it has no hydrogen. And basically this conjugation here, it increases electron density in the ring and facilitates the electrophilic aromatic substitution. To refer to hyperconjugation, we use the term alpha hydrogen. How we use it? Basically, hydrogens on the carbon, like the X here, which is right next to the spot with parallel p orbitals, like this. How many hydrogens are there away from the system, right next to the carbon? We see how many hydrogen. I'm starting to we see how many hydrogens are there right next to the system of parallel p orbitals, and basically that number is what we call the number of alpha hydrogen. And This is basically a hyperconjugating structure. Okay. And just remember that the number of hyperconjugation structures is equal to the number of alpha hydrogens plus 1. Okay. Why plus 1? Because this is the normal base compound. We also consider that a hyperconjugating structure. And these are some extra points. The inductive effect is distance dependent, but the others are distance independent. Okay. And the distance independent clause is true for any effect involving parallel p orbitals. The hyperconjugation we saw here was only the plus H effect, but minus H effect exists as well. It is not in our syllabus. Plus H is an electron donating effect. Minus H is an electron withdrawing effect. And just remember that the only groups that can show minus H are trihalides like CX3, which is connected to anything, where the X can be a halogen like CCl3, CF3, CBr3. These are all minus H effects shown. When multiple effects are applicable on the same compound, we prioritize the resonance effect over the hyperconjugation effect over the inductive effect. And just like the resonance effect, hyperconjugation and inductive effect behave the same way when it comes to ortho and paradirecting or metadirecting. And this is also why alkyls are ortho-paradirecting despite not having any lone pair connected. This I just told you. And hyperconjugation has some other names like no bond resonance and Nathan-Baker effect. But keep in mind that resonance structures are hypothetical and not real. But hyperconjugation structures are real. Yep, they are real. Despite being known as no bond resonance, hyperconjugation structures are real. And hyperconjugation depends on the vibration of the CH bond, like this CH bond, and it becomes less significant with increase in bond strength. Hence, hyperconjugation ability order is greatest of CH bond, then CD bond, then CT bond. Okay. And lastly, electrometric effect. It is a temporary effect. All the others which I studied are permanent effects. Oh, what did I write here? Why did I write nerds? This is needs, okay? Needs. The electrometric effect is a completely temporary effect. Oh, are they? Yeah, so the electrometric effect is a completely temporary effect, while the others are permanent, and this one needs a reagent or it will not work. Okay. It is just the movement of pi electrons in a bond like this when a reagent is added, and in plus E effect, a positive charge is generated and a negative charge in minus E. You can see reagent was added to this unsaturated bond and a plus charge is generated, so it's positive electrometric effect. And this was added, a negative charge was generated, so it's negative electrometric effect. You can even generalize that if a positive thing is being added, it is going to be positive effect, and if a negative thing is being added, it can be negative electromagnetic effect. It's basically a scary name given to a very simple thing. And I think that was it for today's lecture. Sorry for stuttering a lot, but I'm basically done. And how long is this? This is 33 minutes, or it will just write 34. So thank you for attending this lecture, and do let me know your feedback. I will be coming with the second part very soon, and thank you. Please subscribe because I need money to fund my college fee.